Hello class, let's learn about aqueous ionic equilibrium. So really this chapter should have been called neutralization reactions, titrations, buffers, and solubility. And it's really just applying some of the ideas we learned earlier about equilibrium, particularly when we're talking about solubility. And when we're talking about the buffers and the titrations, it's going to be some of that acid-base stuff that we learned about in the preceding chapter. So this idea that we've got an equilibrium expression, if it's a weak acid or a weak base, it's going to dissociate into some products from the reactants. It's going to be a conjugate weak base and a H plus if it's a weak acid, and it's got that Ka with it. And if it's got a Kb, if it's going to be the weak base dissociating into the conjugate weak acid and hydroxide. And then we can do the same thing with soluble salts or sparingly soluble salts. So things that are going to form a precipitate, but usually that precipitate is in dynamic equilibrium, and there will be some of the component ions in solution. And that's the solubility part. How much of a solid can I get into a solution? So why should we study and care about aqueous equilibrium? Well, buffers are incredibly important. Human blood is a complex aqueous mixture containing a weak conjugate acid-base pair and a pH buffered at about 7.4. Imbalance of this equilibrium leads to a malfunctioning of enzymes, resulting in biochemical disasters in the human body. So when you talk about acidosis or alkalosis, and those are serious conditions where the blood's pH is not in that optimal range. That's because proteins are going to have slightly different structures at different pHs because they might be protonated or deprotonated. That's going to affect their functioning. The buffer in blood is very hard to shift around. So all of that stuff about you need to buy alkalized water to adjust your pH and cancer can't survive in an alkali environment, that's all baloney, right? So if somebody's just trying to sell you alkalized water, it's a load of hoo-ha, and don't buy it. Right, so at least don't buy the science or the fake science behind that. Much of the chemical behavior of seawater is determined by its pH. It's buffered to about 8.1 to 8.3 at the surface. If the equilibrium is upset, there's going to be an ecological disaster, so environmentalists are very concerned about that. That's the issue with ocean acidity, right? So as CO2 in the atmosphere increases, it's going to be that atmospheric CO2 will be in equilibrium with carbonic acid or dissolved CO2 in the ocean, and that's going to shift the pH to a more acidic pH, closer to the 7.4 value. So it's going to change that pH. It's going to be more acidic. The corals, which are highly sensitive to pH, are going to bleach. They're going to die out. It's going to be harder for some of those sea creatures to form their little exoskeletons. Formation of stalactites and stalagmites in caverns is dependent on the relative solubility of salts in water that result due to aqueous equilibrium, so geologists, travelers. Sinkholes that result due to dissolution of limestone by groundwater and pose a serious threat to life and property. So engineers, geologists, high school students, when they built our pool at my high school, they built this pool and they literally sunk millions of dollars into it. Literally, because they built the school on the cheapest land that they could get. And so the land was full of sinkholes. So they built the school building where there wasn't a sinkhole. And they kind of forgot about the sinkholes when they went to go build the pool. So they build this pool and they're filling it with water and they're filling it with water and they're filling it with water. And they just keep filling it. And it's like, when is it ever going to end? Turns out, they built it on top of a sinkhole. The pool cracked and all the water drained into the sinkhole. So they had to fill up the sinkhole with concrete, then fill up the pool with water. Fluorides used in toothpaste to prevent tooth decay due to aqueous equilibrium involving fluoride ions. So dentists, right? Remember, HF is a weak acid, right? So it's going to want to hold on to those protons. Well, if you brush your teeth with fluoride, you change some of the hydroxyapatite that makes up your teeth, the bone that makes up your teeth, into fluorohydroxyapatite. It's going to be more resistant to the attack by acid from bacteria excreting acids in your mouth as waste products. So this is your opener, which is the dangers of antifreeze. Every year, thousands of pets and wildlife species die from consuming antifreeze. Most brands of antifreeze are ethylene glycol. Now, ethylene glycol has this molecular structure here. It's got an OH group over here and an OH group over here. Chop one of these off, and I just have CH2. I would have CH3, CH2OH. That would be ethanol, right? So ethylene. It's got 2 carbons in it, and the glycol means it's got 2 hydroxides on either end. The initial effect is drunkenness, because you just chop off one of these OHs, and it's going to look like ethanol. It does taste very sweet because I've tasted it. Don't recommend doing that, but it's metabolized in the liver into this over here, where we convert this hydroxide group, this alcohol group, into a carboxylic acid. And then this is a sample of what somebody filling up their car with antifreeze. And this green color comes from a dye, and that's so that you know what fluid is leaking if you look on the ground. So all those things are color coded, like transmission fluid is red, and antifreeze is green, and your wiper fluid is blue. So why is glycolic acid toxic? Well, in a high enough concentration in the bloodstream, glycolic acid overwhelms the buffering ability of the carbonate in the blood, causing the blood pH to drop. Low blood pH compromises the blood's ability to carry oxygen, resulting in a condition called acidosis. So you've got hemoglobin H+, aqueous plus oxygen gas gives you oxyhemoglobin and H+, right? And so here you've got this H+, right? And that H+ is going to be related to the pH, right? So you could do some common ion effects. What would the Chatelier's principle say? If I change the pH and increase this, right? What do I have to do? I've got to go the other way, right? I can't pick up the oxygen, can't form my oxyhemoglobin, right? That's the form that carries the oxygen if I've got too much H+, right? So causing H+ here, adding product, is going to shift this back towards the reactant. You want this product, right? So it's going to suppress this guy because you've added the H+. One treatment is to give the patient ethyl alcohol, which has a higher affinity for the enzyme that catalyzes the metabolism of ethylene glycol. So, yes, for once, alcohol is the solution. Okay. I'm going to start off with the common ion effect, right? So what we just talked about were this H+, right? And having this extra H+ in here affects the equilibrium, right? Through Le Chatelier's principle. It's called common ion effect, and we're going to see that a couple of times in here because we're talking about aqueous ionic equilibria. And really, the common ion effect is just the same as you would expect from any other equilibrium where you've already got some of the products formed. It's called common ion effect because it's ions that we're talking about. And we should have covered it in the last chapter, but let's start. So we know KEQ is a constant, right? And Le Chatelier says that if a system is stressed, it's going to move to relieve that stress. So if we add stuff to one side of the K expression, it will affect the whole thing. So if I've got this chemical reaction here, where AgCl solid dissociates into Ag plus and KCl, I've got a KEQ for this, which is Ag plus times Cl minus over 1, because this is a solid. And later on, we'll call this KSP. Let's give it a fancy name for it, just KSP. So if the Cl minus ion concentration goes up, the Ag concentration goes down so that K is constant. Right? The same thing would happen if I added in Ag instead. Right? So if I added in some extra Ag, my Cl minus ion concentration would go down. In other words, the concentration of the whole thing, the other thing, will go down, and the math actually gets easier because you don't have to do if I wanted to figure out the concentration of one of these things, right, I could set up an ice table and do X times X is equal to K, right, products over reactants is equal to K, and I have to do the square root, right, well, if I already know what the value of one of these is, right, it's just going to be K is equal to X times some number. Right. So here we would have a fixed chloride ion concentration, and we tried to solve for the Ag concentration. Right. So let's say I've got AgCl in a flask, and I add 0.02 molar sodium chloride. What's the concentration of silver plus in solution? And this is a reaction that you're going to see again If you take analytical chemistry with me, we're going to do a lab on precipitation gravimetry, but we're actually going to do the opposite. We'll add an extra Ag instead of extra Cl because we're trying to capture the Cl. All right, so here's my KSP, 1.7 times 10 to the minus 10. Our plan is we'll set up an ice table because it's a regular old equilibrium problem. Usually that means we've got to do a quadratic to solve, but in this case, because the concentration of one of the things is given and it's so much higher, it makes the math a lot easier. So our balanced chemical equation is AgCl solid goes to Ag plus and Cl minus. Our K expression was K is equal to Ag times Cl over 1, or 1.7 times 10 to the minus 10 is equal to Ag plus times Cl minus. We know the Cl minus concentration was 0.02. Rearrange to solve for Ag, and we end up with 9.9 times 10 to the minus 9. This concentration is a whole lot less than it would be if it were in just by itself, if I just had the Ag and Cl with no common ions. So if I put in something that was not common to either of them, like potassium nitrate, I would have... Right, so if I added potassium nitrate, my concentration of silver would be the square root of K, or 1.3 times 10 to the minus 5. So I got 1.3 times 10 to the minus 5 with no common ion. If I add the common ion, it is a lot less. Here, 8.9 times 10 to the minus 9. So it's 4 orders of magnitude less if I've got this common ion there. Okay. Setup is pretty easy, right? So if there's no common ion, the concentration is just the square root of K, right? Concentration of Ag would just be the square root of K. If Cl minus is common, so if I added 0.1 molar NaCl, well, now I set up my equilibrium expression just like I did before, but now I've got this 0.1 molar here, whatever the concentration of the common ion is. My concentration of the other thing is K divided by that concentration of the common ion. Right. That's if we're doing this, this particular setup, right? So if I had something that doesn't have one in there, I would have, I'd have to worry about the reactants as well. If Ag is the common guy, well, if I've add 0.1 molar AgNO3, there's a lot more Ag from the AgNO3 than there would be from the dissociation of the silver chloride. So my concentration is going to be 0.1 plus X, and X is going to be really, really, really small, right? On the order of times 10 to the minus 9. Right? So it's not going to move this 0.1 around. Right? We can do this with acids and bases as well. So for example, if I've got 0.1 molar acetic acid, its pH is 2.89. But what if I've got a mixture of acetic acid, 0.1 molar acetic acid, and 0.1 molar sodium acetate dissolved into 1 liter? All right, so I'm going to set up an equilibrium expression on an ice table just like I would for the acid form as a weak acid. But now, so I'm going to set it up where I've got my concentration of acetic acid, and then I've got a concentration of acetate in here as well. Lose a little bit, gain a little bit, gain a little bit. I'll end up with the initial concentration of the acetic acid minus X, X for the concentration of H3O plus, and the concentration of the acetate for the acetic acid, or the acetate concentration at equilibrium plus X. Set it up in my K expression, products over reactants, H3O plus, conjugate base over conjugate acid. Put in the actual numbers. X is going to be small because our initial concentration is large compared to the K value. So I end up with X times 0.01. This is my base concentration over my acid concentration. Solve for X, 1.8 times 10 to the minus 5 molar. I get my pH, which is the minus log of that, and my pH is 4.74. So why is there a difference in pH? Right? Well, your first blush is going to be, well, I've got my weak acid, right? It started off at about 2.8, and I'm adding in some of the conjugate base. Well, I'm taking a weak acid and a weak base, combining them together. It should be a little bit more basic than the weak base. Yes, that's true, right? The other way to think of this is as Le Chatelier's principle. If I add in stuff here on this right-hand side, right? And it's going to push the equilibrium back to the left. What's going to happen to this concentration of this other product? It's going to drop, just like we saw with the acetate. And we can plot this out as a function of added acetate concentration. And this is actually going to be a really good segue into our next subject, which is neutralization reactions.